Hi there. In this video, we're going to talk about the strong law of large numbers. Many students and professionals encounter the phrase law of large numbers, but might not know what it really means or why it's so crucial. It's a cornerstone of probability theory, underpinning everything from predicting stock market trends to quality control in manufacturing. In this video, we'll break down what is the strong law of large numbers. We'll explain what it means mathematically and explore why it works. We'll also look at practical examples and see how this law plays out in real life. The strong law of large numbers is actually one of the cornerstones of probability and statistics. It basically guarantees that under certain conditions, the sample average converges to the expected value almost surely as the sample size becomes infinite. Let's define the strong law of large numbers formally. Suppose we have x1, x2, 3, and so on. This is a sequence of independent and identically distributed random variables with mean mu is equal to the expectation of x, and also a finite variance sigma squared. The mean that we've just referred to now is the true mean. So the strong law of large numbers states that as the sample size grows, the sample mean x bar n, which is the sample mean, this will almost certainly converge to the true mean mu as n becomes very large. So here the notation, the arrow with the as above it, means almost surely. This is something that's used in probability theory, and all it means is that the probability of this particular convergence is 1. Now, let's try to understand intuitively what all this means. Let's say we roll a 6-sided dice. In the last video, we looked at what expectation is and how it's determined. We saw how to determine the expectation for this particular example. When you roll a standard 6-sided dice, the possible outcomes are 1, 2, 3, 4, 5, 6, and each outcome is equally likely. The expected value is a weighted average of all possible outcomes, where each outcome is weighted by its probability of occurring. In this equation, the small letter xi is the possible outcome, that's either 1 to 6, and p of xi is the probability of each face of the dice, which we know is 1 over 6. When we apply this formula and substitute in all of these values, we see that we get 1 over 6 into 21, which is 3.5. So the expected value is 3.5. So even though 3.5 isn't a possible outcome of a single roll, it's the center of gravity of the distribution of outcomes. It's sort of like a balance point considering all the probabilities. So this expected value 3.5 is what we refer to as the true mean. So where the strong law of large numbers comes in is when we start comparing the sample mean to the true mean. So let's see practically what happens. Let's say we roll our dice 10 times. We have now plotted a graph where the x-axis is the particular roll of the dice and the y-axis is the cumulative sample average, or rather just the sample mean. The curve shows how the average is changing as we increase the number of rolls of the dice. So that dashed line that you see is the expected value or true mean of 3.5 that we have just calculated. So now let's say we do 100 rolls and then we plot the same thing, that same graph. So on the x-axis, the range of values we can see goes up to 100. Now what do we see? We see that the curve, which represents the sample mean, it fluctuates quite a bit, and that fluctuation is quite significant for the first maybe 40 rolls or so. After that, the fluctuation starts to reduce as the number of rolls get bigger and bigger. Finally, let's now look at 1,500 rolls of the dice and what happens when we plot that on a graph. We can see that the x-axis goes all the way up to 1,500. But we see that beyond a certain point, there is virtually no fluctuation in the sample mean, and that the sample mean has become the true mean or expected value of 3.5. We see that the curve has become that dashed line. So why does this happen? So imagine each random variable as a small piece of information about the true mean. When you average many values, the random deviations cancel out, leaving you closer to the expected value. So mathematically, this happens because the variance of the sample mean decreases as the sample itself increases. We'll now look at a practical example of the strong law of large numbers applied in engineering. Imagine a factory producing steel rods for construction. The rods are designed to have an average length of 100 centimeters. So in engineering, the true mean is not determined in advance like we are done with rolling the dice. In engineering, the true mean mu is something that we specify as part of the design process. So we say in advance, we want the true mean to be 100 centimeters for this particular rods. So it's the expected value based on the manufacturer's requirements and the value that the process is designed to achieve under ideal conditions. But we know, of course, that no process is perfect. Each rod might be slightly longer or shorter due to random factors like machine vibrations or inconsistencies in the material. So due to machine variability, each rod may slightly deviate from this target of 100 centimeters. So quality control requires checking if the manufacturing process is consistent with the specified average. So over time, the lengths of the rods in centimeters are measured. Suppose the measured lengths for the first 10 rods are as seen on the screen. We can then determine, using this sample, what is the average of this sample or the sample mean for these different values of n, which is the number of rods produced. The sample mean for the first rod is simply 100.5 centimeters because it is just one value. For the second, what we'll do is we'll take the first two values of n, then we add them together and divide it by 2 to get the sample mean, and we see that it is 100.15 centimeters. And then we'll do the same for the third rod. We'll take the first three values of n, add them together, and then divide it by 3. And we see that we get a value of 100.13 centimeters. So we can carry on determining the sample average like this, and eventually we can do it for the final rod. We'll take all 10 values, we'll add them together and divide it by 10, and then we see that the sample length, average length, is 100.11 centimeters. So there is very clearly a pattern emerging. We have 100.5, then we have 100.15, then 100.13, and then 100.11. So the values are clearly decreasing as the number of rods are increasing. In other words, the lengths of the individual rods fluctuate around the target. But as n, the number of rods measured, as that increases, the cumulative average or the sample mean, what it does is that it converges to the true average length, which is that 100 centimeters, that design value. So this is the strong law of large numbers in action. With more samples, the sample mean approaches the population mean or that true mean. If we went beyond 100 rods and we looked at 1,000 rods, the sample mean would probably be very close to 100 centimeters. This is very insightful because what it means is that engineers can rely on the strong law of large numbers to verify that production processes meet specifications over time. For instance, if the true mean length of rods is consistently near that 100 centimeters, the manufacturing process is operating correctly. If not, then engineers can see that maybe some adjustments is needed for the process and maybe some maintenance of the equipment is required, maybe calibration of all the machines in the factory. So to summarize, the strong law of large numbers guarantees that the sample averages converge to the true mean as the sample size becomes very large. This concept is foundational in probability and statistics, with applications in nearly every field. So in this video, we've seen the formal definition, we've explored the intuition behind it, and then we looked at real-world examples and uses. So whether you're rolling dice, managing a factory, or predicting election results, the strong law of large numbers is at work. Thank you very much for watching. Please like and subscribe if you found this video helpful.